All right, free energy of dissolution. So we've talked about delta G, and we've been kind of vague about it. We're focusing on how delta G is really the accumulation of enthalpy, entropy, temperature. And so we're going to focus specifically on a delta G that's related to dissolution. When we're talking about delta G, we need to focus on the different thermodynamic quantities. And so we're just recapping this once again. So enthalpy is delta H, and delta H is related to potential energy. We have the potential energy of the products and the reactants, and we can look at that via data, or we can look at it on the graph right here. So we have the potential energy of the reactants, we have the potential energy of the products, and we can calculate that using the delta H. As a reminder, we have exothermic, where energy is released, and then we have endothermic, where energy is entering the system. And you need to know exo is negative, endo is positive, just to show direction. Entropy is delta S, and we're seeing how chaotic something gets. We're seeing the randomness, the disorderly. If we have a positive delta S value, that means it's getting more chaotic. So you can see like blocks, for example, where they're thrown about. If you have something more orderly or less chaos, so it is organized like this, I had to put energy in order to make it organized, then that is designated with a negative delta S. And so we have gives free energy. So we've talked about delta G. It's the energy involved using both of the thermodynamic values that I talked about earlier. And so we're going to be very specific in this section. And so just again, as a reminder, it's the energy involved for a reaction to thermodynamically happen or not. And so if we have a negative delta G value, that means it's going to be spontaneous. It does not need to put more energy involved into it. It will just happen naturally. As a reminder, College Board does prefer you to use the term thermodynamically favorable. Spontaneous is a word that you'll hear a lot if you're using other things to learn stuff for this class, but College Board wants things to be very, very, very specific. But honestly, like, you're going to see the word spontaneous in college, so just know that you can use spontaneous for your own remembering of stuff. But for some reason, College Board really wants you to know it's thermodynamically favorable. Cool. And so delta G is positive. That's non-spontaneous, so that means it's not going to happen unless you input some energy involved, and so you should say that it's thermodynamically unfavorable, non-spontaneous. And so an example of this is batteries. So we have batteries inside our appliances, so when it's inside the appliance, you have that spontaneously happening when you input a button press or whatever, versus the battery itself. The battery has the reaction that's happening in it, and then you can see if it's spontaneous or not. Like, is it naturally going to happen over time versus did I need to input energy involved to make that reaction actually do its thing? For this particular section, we're going to focus on dissolving salts. And so we know that salts can either really be soluble or they can be ever so slightly soluble. As a reminder, when we say something is insoluble, technically, because of equilibrium, you have a tiny, tiny, tiny bit that's actually dissolving. So that's why we'll say slightly for the purposes of this, because now we know equilibrium. And so it is based off delta G. And so as a reminder, delta G is showing if it's thermodynamically favorable or unfavorable. And so we can see a salt dissolving that way. And so as a reminder, we have this formula we learned earlier where it's involving delta H, we have temperature, and then delta S. And so all of these state functions affect delta G, and we're going to see how that is implemented when dissolving a salt. And so we have in dissolving two processes. So we can either have the positive parts or the negative parts, and then we're going to see how our delta G gets affected by the negative parts and the positive parts. And so for a quick little your turn, decide delta G. If delta G is positive, does that mean the salt is slightly soluble or the salt is very soluble? And then for the opposite, where delta G is negative, is it slightly soluble or soluble? Go ahead and pause, and then I'll answer in a second. Okay, so because delta G, when it's positive, is unfavorable, that means the salt will only slightly dissolve. Versus if delta G is negative, then you end up having a salt that is soluble. Okay, so when we're talking about dissolution, and so dissolution is just the term for, hey, a solute, in this case it's going to be the salt, and then it's dissolving in a solvent. In this case, we almost always use water, and we're making a homogeneous solution. And so in this case, we're making salt solution. And so when we're looking at dissolving a salt, we are looking at a couple factors. So we're looking at breaking IMFs. We have the IMFs within the salt. We have the IMFs within the solvent. We also have some other parts. So we have the organization of the solvent around the dissolved species. So since we're talking about salts, we're usually going to talk about ionic stuff. And so when the ionic compound breaks apart into its dissolved ions, we're going to see the solvent, aka the water, surrounding that ion. And so we'll see the interaction between that solvent. So again, in this case is the water, and we'll see the dissolved species. But what does that even mean, right? Because that can be a little confusing, and so I'm going to go over that with a couple examples. When salt dissolves, we break IMFs. We're breaking the ionic bonds that are in between the different ions. We're breaking the hydrogen bonding, which is an IMF, not a bond. And so those are breaking. And then we have the IMFs that are forming between the ion and the dipole of the water. But I'll talk about that more in depth the next slide. And so because we have to talk about IMFs, we're going to use that Unit 3 knowledge that we know, and then we're going to apply it to delta H and delta S. And so before I do that, I think this diagram is really good. It summarizes exactly what I said earlier, but I want to see if y'all can figure out what is slightly wrong about it. So go ahead and pause the video and try to figure it out. Ready? All right. So sodium ion and chloride ion are not the same size. If I think about Bohr's model, I can think of sodium. Sodium is going to have 2 energy levels because it lost a valence electron. And then chloride has 3 energy levels that are fully full. And so 2 versus 3, chloride is going to be bigger. So you want to keep that in mind. But besides that, again, looking at this diagram, it does explain in summary what's happening. So we have the salt and we're breaking it apart. We see the ion here. It is being surrounded by water, and the chloride ion is also doing the same thing. So when we're dissolving a salt, we can talk about delta H because enthalpy is delta H. And so again, there's a couple factors involved. So I have delta H. It is positive when you're breaking the attractions. I'm saying attractions vaguely because it depends on which attraction I'm talking about. So an example of this is here. We have the NaCl, so it is a salt. And so we have the sodium and the chloride, and those are breaking apart. The ionic bond, or the ion-ion attraction, is breaking apart. In order to break apart, energy is needed to be inputted to break that bond. So that is one attraction that is breaking. We also have the attractions between water over here. And so the water over here has hydrogen bonds. As a reminder, hydrogen bond is not a bond, it is an IMF. And so it is an IMF between a hydrogen that happens to be bonded to an oxygen in the molecule, and then it's attracted to another highly electronegative element here. And so that is breaking apart. So that's the two main things for dissolving a salt in terms of IMFs breaking apart. So that is that. We have the attractions that happen between the water and the ions of the salt. So when the ions of the salt are broken apart, we have ions that are separated. And so we have the water surrounding the sodium, and then we have the water surrounding the chloride. Now, obviously, I did talk about the types of attractions that are breaking and forming literally just now, but just to make sure that you're paying attention, why does this happen? So go ahead, pause the video, think about it yourself before I talk about it. Ready? Okay. So we have water. Water has a dipole, aka a polarity to it. We have the partial positive sides, which are the hydrogens, and then you have the partial negative side, which is the oxygen. As a reminder from Unit 3, the dipole is created because the electrons in this bond are shared unevenly. The electrons tend to go towards the more electronegative element, and so in this case it's going towards that oxygen. So that's why oxygen tends to be partial negative and hydrogen tends to be partial positive. So you can see over here you have the symbol, the delta negative symbol on the oxygen part of the water, and so since it's partially negative, it is attracted to the positive of the sodium ion. You could say the same thing for the chloride. So the chloride has a negative ion, right? Negative charge. And so we have the partial positive of the water, and it's pointing there because it's being attracted to that. Because of these attractions between the water molecule and the ions of the salt, that makes a negative delta H. And so you have to, again, remember when you break those attractions, so again, either the ionic bond or the hydrogen bonding of the water, that is delta H, that's positive because you broke those attractions. But you're forming new attractions between the ions and the dipole of the water. And so that is a negative delta H. And so we need to figure out if the enthalpy of dissolution is exo or endothermic overall, because we have both happening. We have attractions that are breaking and attractions that are forming. And so there's multiple ways that this can be asked. So for example, you could just be straight up given the values, or you might need to calculate delta H based off values that are given to you. So you should be able to do both depending on what's happening. But from just looking at this, you would not necessarily know if overall this is positive or negative, because again, there's different values for breaking attraction versus forming, who's involved, what species is involved, and so on. So for delta H dissolution, we have endothermic, which is a positive value, and so you know that the enthalpy change does not contribute to favorability because that's inputting energy overall. If delta H dissolution is exothermic, aka negative, that means the enthalpy change does contribute to favorability because it is releasing energy. I didn't need to input energy overall in order for this to actually occur. So now we can talk about entropy of dissolution. Remember, entropy is delta S. And so we have breaking attractions, which is a positive delta S. As a reminder, a positive delta S value means it's less orderly, it's more chaotic, it's more random. And so we can look at that with this diagram here. So in this part right over here, we have liquid water. And so when we break the hydrogen bond attractions, the IMF, then that means that these water molecules are going to get more chaotic, more randomized in terms of where they are. Same goes for the sodium chloride. You can see right here, sodium chloride is super duper organized. It is a pattern that repeats itself one by one by one by one. And so when I break that ionic bond, it's not organized nicely anymore. And so it gets really random. And so that's why it's a positive delta S. So when we break those attractions, it is positive. When we form attractions, it's going to be negative delta S, because as a reminder, negative delta S is about reorganizing it. We are technically constraining the particles' movement because they're moving in a way where they're attracted together, and so it's going to be more organized, less chaotic. And so going to, again, this diagram here, we have the sodium ion that was separated, but now is attracted to the partial negative side of the oxygen here. And so the water molecules are going to surround that sodium ion again because opposites attract. That forms a structure that looks very organized because, again, the ion versus the partial negative is attracted. You can apply the same situation with the chloride ion over here. And so the chloride ion is negative. We have the partial positives of the water. And so the positive and negative parts are the ones attracting to each other. Similarly to delta H, we need to figure out overall what's happening. We have both of these things happening because we have to break attractions and form attraction, but we need to see entropy overall. So after everything happened, is it going to be more positive or negative? We can either be given these values or we need to calculate it in some way. Again, similar to the delta H from earlier. And so overall, if the delta H dissolution was positive, then entropy does affect the thermodynamic favorability of the process that is happening here. Versus if it is a negative delta S, the entropy does not affect the favorability of this reaction thermodynamically. So we've talked about this formula before. And so now you need to think about the formula and who's involved. So overall, the delta G, if it's positive, dissolving is not thermodynamically favored. But if it's negative, then it is thermodynamically favorable. And so since we've talked about these two components in huge detail, the delta H and the delta S, the FRQs or MCQs that could be related to this is going to be heavily assuming you know what is happening. So make sure that you can talk about the diagrams, or if there's no diagrams, talk about the process of all of the attractions that are breaking and forming and how it affects the delta H and the delta S. So now I'm going to summarize what I just talked about. So we have the three main steps that are happening. We have the ions that are separating in the salt. So that's the solute. Then we have the solvent, in this case water, is separating in some way. And then we have the salt ions and the solvent water, and then they're going to form an attraction. And so when I'm looking at this first step one, we have a positive delta H. Since we've had to separate those ions, we had to input energy, and so inputting energy is going to be positive. We have our entropy, which is also going to be positive because it's getting more random. It is getting more chaotic. In step two, we're also separating the IMFs of the water, so that's going to be positive, and that's going to also be a positive delta S because that is also increasing the randomness. But when we have the solute and the solvent forming an attraction, that's going to release energy, which is why it's negative delta H, and then it's also going to get more orderly, and so that's going to be a negative delta S. So you should be able to describe, like I said, what's happening, and then talk about why its delta H is positive or negative, and why the delta S is positive or negative. A bonus thing that you should know is on step 3, I said it's forming an attraction. You should know that it's forming an IMF, but it's specifically forming a dipole ion interaction or a dipole ion attraction. That is the specific IMF that we're talking about here. Will the salts actually dissolve or not? It depends overall what's happening with the delta H and the delta S, and so we have to see how the values calculate the delta G, and then we can say, will it dissolve a lot or a little bit based off what I said earlier. So you should be able to explain how solubility works with salts, and then how does it change with enthalpy, which is delta H, and entropy, which is delta S. And so we also should be able to calculate using that formula depending on how we've gotten the delta H and delta S values. For example, if this was a multiple part FRQ, then the delta H might have been calculated in one part, the delta S might have been calculated in another part, and you should be able to input those values. On the flip side, maybe they don't give you values, and you should be able to logically explain, well, if delta H was very positive and delta S was very negative, or something like that, what would the delta G end up being? When I mean everything connects to everything, we have learned so many things this year. We have learned Unit 1, where we saw how things bonded ionically. We've also talked a little about covalent stuff. We talked about it way more in Unit 3 when we were talking about IMFs. We have stuff in Unit 7 that we can apply to this unit that I'll talk about in a second. And then obviously we just learned Unit 9 stuff like entropy. And so if delta G is positive, that means it is not thermodynamically favorable, or we could say thermodynamically unfavorable. You will say in other places, like in college or whatever, you might say not spontaneous. And so your salt is slightly soluble, like barely. And if I bring out Unit 7, that means our KSP value is going to be very, very, very small, going to be way less than 1. But if I have the opposite, where delta G is negative, that means it will be thermodynamically favorable. And so it means that salt is soluble, and so that K value is going to be bigger, usually bigger than 1, but some value that is bigger. Now, because we had that formula earlier, that delta G equals delta H minus T delta S, technically, we can have an endothermic process, so the salt can dissolve endothermically, but we can still have a negative delta G if a lot of chaos happens, or a lot of, the randomness happens, where it is decreasing that order. And so if that disorder, that randomness is so big compared to how much heat energy you needed to input in the process, that means your delta G can be negative. And so you want to make sure that you can apply that. So if they, sometimes College Board will ask a question on an FRQ that says, can this happen? Well, yeah, if you have enough of the craziness of the particles as movement and whatnot. And so you want to make sure you can explain that. Cool. So overall, everything connects to everything, as I said. And so sometimes it'll take a while. We'll do some practice on this and stuff, but hopefully you got the gist of it. Okay, bye!